All right, today we're diving into something that powers, well, pretty much everything. But maybe not in the ways you think. We're going to go on this kind of unseen journey to figure out how electric charge actually moves through solids, liquids, and yeah, even thin air. So when you think electricity, what pops into your head? A copper wire, right? But honestly, that's just scratching the surface. Charge can flow in some really surprising places. So the real question is, how? How does it actually do it? All right, let's get into it. Okay, let's start on familiar ground, solid metals. I mean, this is the bedrock of our electrical world, right? But the way charge moves here, it's this fascinating, kind of microscopic dance. So inside any metal wire, you've got this fixed, repeating structure of atoms. Think of it like a jungle gym. It's called a crystal lattice. But here's the cool part. Not everything is locked down. Let's meet the main character for this part of our story, the conduction electron. These little guys are totally free to just roam around this lattice, and they're the ones carrying the charge.
You know when you flip a light switch, the light comes on instantly. It feels like electricity is zipping along at the speed of light, doesn't it? Well, here's a fact that's going to bake your noodle a little bit. The individual electrons, they're actually crawling. I'm talking millimeters per second. It's a snail's pace. We call that their drift velocity. So what gives? The instant effect you see isn't about the speed of one electron, it's about a chain reaction. The electric field itself gives an instant push to all the electrons in the wire at once. It's just like a long line of dominoes. One pushes the next, and the effect at the end is immediate.
Ever wonder why your phone or your laptop gets warm? Well, it's because those drifting electrons are constantly bumping into the atoms in the wire. It's like microscopic friction. That's electrical resistance, and it's basically just wasted energy that turns into heat. But what if you could build a perfect, totally frictionless highway for them? Well, that's exactly what a superconductor is. You cool it down below a very specific critical temperature, and bam, the resistance just vanishes. Completely. Electrons can just glide along forever with zero energy loss. It's wild. And this leads us to one of the coolest properties of metals for sure, the thermoelectric effect. And really, it's a two-way street. First, you've got the Seebeck effect. You just heat up the spot where two different metals touch, and boom, you generate a voltage directly from that heat. But here's where it gets really crazy. It works in reverse. That's the Peltier effect. You can apply voltage to that same junction, and it becomes this tiny, precise heater, or cooler, all with no moving parts. Just incredible. Okay, time to move on to our next state of matter. Let's see how this all builds. We're leaving the neat, tidy world of those crystal lattices, and we're diving headfirst into the, let's call it the chaotic world of liquids. And in here, a whole new cast of characters takes over the job of carrying charge. In liquids, we've got totally new charge carriers. So forget about those free-roaming electrons for a minute. Here, it's all about ions. You know, atoms that have either a positive or a negative charge. So when you dissolve something like salt in water, what you're really doing is creating an electrolytic solution. And it's just teeming with these free-moving ions, all ready to carry a current.
And when you pass a current through this solution, you kick off this chemical reaction called electrolysis. It's pretty straightforward. At the positive terminal, the anode, ions get oxidized. That just means they lose electrons. And over at the negative terminal, the cathode, ions get reduced. They gain electrons. The key thing here is that you're not just moving charge around anymore. You are fundamentally changing the chemistry of the solution itself.
So you have electricity, right? We measure that in units of charge called coulombs. And then you have chemistry, which we measure in amounts of stuff called moles. So how do you connect those two worlds? Well, this number is the answer. The Faraday constant. Think of it as nature's official exchange rate. It tells you exactly how much charge you need to transform a specific amount of a chemical. It's like the universal translator that lets us speak electricity and chemistry in the same sentence. It's a huge deal. And this chemistry, this is the entire principle behind batteries. I mean, a primary battery, think of your standard disposable AA. It runs on a chemical reaction that can only go one way. Once the chemicals are spent, that's it. It's done. But a rechargeable battery, what we call an accumulator, uses this really clever reversible reaction.
When you plug it into the wall, you're applying an external current that forces that chemical reaction to run backward, basically restoring the original chemicals so you can use it all over again.
Okay, we've seen charge kind of shuffle through solids and swim through liquids. Now it's time for the most dramatic journey of all. We are going to force electricity to do something it really, really doesn't want to do: travel through a gas. And remember, a gas is normally an amazing insulator.
So, how in the world do you make electricity jump across thin air? Normally, you just can't. A gas is a fantastic insulator. To force it to become a conductor, you have to hit it with a ton of energy, enough to literally rip its atoms apart. You got to make it jump that gap.
So how does a spark actually form? Well, first you need a seriously high voltage. Then you need a trigger. And get this, it can be something as small as an ionizing agent, like a cosmic ray that's traveled all the way from deep space. It zips in, knocks an electron off a gas molecule, and creates the very first free ion. That high voltage then grabs this ion and accelerates it, making it crash into other molecules, which creates this avalanche of more ions, forming a conductive path. And then, zap, you get that sudden, brilliant, visible electric discharge. A spark.
And this process, discharging electricity through a gas, it unlocks some really amazing stuff. If you control it just right, you get the steady, beautiful glow of a neon sign. But it also creates light, makes even more ions, and can even generate these beams of pure electrons we call cathode rays. And these rays, they weren't just some lab curiosity. Their discovery literally paved the way for things like old-school CRT televisions, and, more importantly, it was the first real proof that the electron even exists. All right, so we followed charge as it shuffles through solids, swims through liquids, and leaps through gases. Now, let's bring it all home. Let's see how mastering these different types of conduction has given us some of the most powerful and important technologies we have. Take a look at a fuel cell. This piece of tech is just a beautiful combination of our entire journey today. You see, it has a solid anode and a solid cathode, just like in our first section, but they're separated by an electrolyte, which could be a liquid or a special kind of membrane. And it uses those principles of electrolysis we saw in liquids to combine a fuel with oxygen, producing electricity directly. It's the whole package.
I mean, really understanding this journey has had massive, massive implications. We use thermocouples based on that Seebeck effect for incredibly precise temperature measurements. The reversible chemistry of lithium-ion batteries, that powers everything from your phone to your car. And maybe one of the most incredible applications of all, we use the thermoelectric effect in reverse to power deep space probes like Voyager. It literally turns the heat from decaying radioactive material directly into electricity, keeping those probes running for decades. Amazing.
When you get right down to it, understanding these fundamental ways that charge moves, that's been the key to so much of our technological progress. We've learned to guide electricity through solids, through liquids, and through gases. So it really makes you wonder, what's next? Are we going to be building circuits out of plasma, the fourth state of matter? Or maybe find new ways to harness the quantum world itself? The journey of charge, it's far from over. Thanks for joining me on this one.